I've always studied the laws of physics. I've always been curious about how the universe works, where it comes from, what are the rules that govern the behavior of the universe at the deepest level. And so I do physics for a living. I study cosmology and the Big Bang and what happened before the Big Bang, if anything. But it's a system of things that hooks up in very complicated ways to our human scale lives. There's the natural world that scientists study, and then we are part of the natural world, we human beings. So there's an old creationist myth, right, that says that we live in a universe governed by the second law of thermodynamics. Disorder or entropy grows with time, from early times to later times. So if that were true, how in the world could it be the case that here on Earth something complicated and organized like human beings came to be? Now, there's an easy, simple response to this, which is that the second law of thermodynamics says that things grow disorderly in closed systems, and the Earth is not a closed system. We get energy in a low entropy form from the sun, we radiate it out in a high entropy form to the universe. But okay, there's still a question, even if it's allowed for structure to form here on Earth, why did it? Why does that actually happen? Is that something natural? Is that something that needs to be guided, or does it just kind of happen? And in some sense, this is a physics problem. So I've become increasingly interested in how the underlying laws of physics, which are very, very simple and mindless and just push particles around according to equations, take us from the very simple early universe near the Big Bang, after 10 to the 100 years, to the very simple, expanding, desolate cold of empty space in our future, passing through the current stage of the history of the universe where things are rich and intricate and complex. We know there's a law of nature, the second law of thermodynamics, that says that disorderliness grows with time. Is there another law of nature that governs the complexity of what happens, that talks about multiple layers and structures and how they interact with each other? And, embarrassingly enough, we don't even know how to define this problem yet. We don't know, the right quantitative description for complexity. So part of what we're doing is, this is very early days, right? This is Copernicus, not even Kepler, much less Galileo or Newton. This is sort of guessing at the ways to think about these problems. You can think about the universe as a cup of coffee, that you're taking cream and you're mixing it into the coffee. When the cream and the coffee are separate, it's simple and it's organized, it's low entropy. When you've mixed them all together, it's high entropy, it's disorganized, but it's still simple. It's in the middle. When the swirls of cream are mixing into the swirls of coffee, then you get this intricate, complex structure. And you and I, human beings, are those intricate whirls in the cup of coffee. We are the little epiphenomena that occur along the way from a simple low entropy past to a simple high entropy future. We are the complexity in the way. And that's sort of a nice physical description. It also makes you think about things beyond the simple physical description. It's talking about human beings suddenly. There's questions here about the origin of galaxies, the origin of stars, the origin of life. There's also questions about the origins of thought and cognition. There's also questions about the origin and the role of meaning and mattering and purpose in the world. I think that, my sort of medium-scale research project these days is understanding complexity and structure and how it arises through the workings out of the laws of physics. My bigger picture question is about how human beings fit into this. We live in part of the natural world. We are collections of molecules undergoing certain chemical processes. We came about through certain physical processes. What are we going to do about that? What are we going to make of that? Are we going to dissolve in existential anxiety, or are we going to step up to the plate and create the kind of human scale world with value and meaning that we all want to live in? My own work is the traditional classic pencil and paper theorist. I own a computer. I mostly use it for email and looking at the internet. What I actually do for a living is take pieces of paper or a blackboard and I write equations. So my job is to take an idea, turn it into equations, and then use those equations to make predictions, hopefully to connect with the world that we see around us. So I'm a member of the physics department and the theoretical particle physics group at Caltech in Pasadena. And most of us there in that group are people like me. We're sitting at our desks, we're chatting to each other at whiteboards or going to Starbucks over coffee and saying, What if we added a certain field to the inventory of the universe that interacted with other fields in such and such a way? Would that help us understand the dark matter? Would that help us understand the dark energy? Would it help us understand the mass of the Higgs boson, for example? So the general field in which I'm working is one that is tightly influenced by experiments, discovering the Higgs boson, discovering the patterns in the microwave background, the leftover radiation from the Big Bang. We would like to take these clues that the universe is giving us and turn them into quantitative theories for how the universe works. And that's sort of the traditional understanding of what my job is. I talk to other theorists, I have graduate students. People always ask whether I have a lab. No, I do not have a lab. I have an office with a desk. I am lucky enough to be sitting at the desk that Richard Feynman sat at back when he was a professor at Caltech. When people ask me why, I explain to them that Feynman's desk gets given to the physicist, the most senior physicist who is not senior enough to warrant a brand new desk. So that turns out to be me at Caltech right now. But I am increasingly getting interested in a different kind of physics theorizing that is not just writing down a new set of fields or a new model for particle physics or cosmology, but taking the models we already know and sort of looking at them at a slightly different level of abstraction. Thinking about the robust features of entropy and complexity and how they play together. So just as one example, some colleagues of mine and I are writing a paper which we call the Bayesian Second Law of Thermodynamics. This is taking Bayes' theorem, which is a result in statistics. You want to update your likelihood, your belief in a certain theory based on the information that you get, the data, the observational outcome. So Bayesian statistics is a very traditional way of thinking about the increase of scientific knowledge. We start from some possibilities, we learn more and more because we collect new data. In some sense, this is what you do every time you look at any physical system. You thought it had certain properties, you measure something about it, you learn more about it. So we're marrying Bayes' theorem in statistics to the second law of thermodynamics in physics, and we're getting a new way to think about microscopic systems that you can actually measure in the lab. We're learning a lot about how the fundamental laws grow into the macroscopic laws. And one of the interesting things at a philosophical level, just as much as a scientific level, is the role of causation or causality. What causes what in the natural world? It's fascinating to a lot of people when you open up a book on quantum field theory or particle physics. Words like cause and effect appear nowhere in a traditional particle physics book. The notion of causality is not there. It might be misused a little bit to sort of stand in as something that says signals do not travel faster than the speed of light. But the idea that A precedes B and therefore A causes B is a feature of our big macroscopic world. It's not a feature of particle physics. In the underlying microscopic world, you can run forward and backward in time just as easily as one way as the other. So this is something we all think is true. It is not something we really understand at a sort of level of deriving one set of results from another. If you want to know why notions of cause and effect work in the macroscopic world, even though they're absent in the microscopic world, no one quite understands that. It has something to do with the arrow of time and entropy and the growth of entropy. And this is a connection between fundamental physics and social science. And, working out in the world of sociology or psychology, why does one effect get traced back to a certain kind of cause? A physicist is going to link that to the low entropy that we had near the Big Bang. Cosmology, which is sort of my home turf, is in a very interesting situation right now. Like, remarkably, to anyone who was around when I was in graduate school, we understand so much about the universe now that we didn't understand 20, 25 years ago. We understand its overall density, its likely future fate. We know a lot about the primordial conditions and so forth. And this has put us as physicists in an awkward position. We love understanding things, but it makes it hard to make progress. You make progress when there's something you don't understand, some puzzle that is being given to you. And the kinds of puzzles we have from the data right now in cosmology are sort of so big picture, so non-detailed, that it's hard to know how to move forward. Why does the energy of empty space have the value it does? Why did the early universe have such a low entropy? So we have ideas about this. The most famous single idea in sort of modern theoretical cosmology is inflationary cosmology. The idea that in the very early universe, it was almost unimaginably tiny, but it inflated by an enormous amount in a very short period of time, and it smoothed out and became the universe we see today. It's a very powerful idea, traced back to Alan Guth at the late 1970s, but it seems to have an unfortunate or fortunate consequence, depending on how you want to spin it. Namely that inflation takes this tiny region of space, makes it really big. Part of that really big region becomes our universe, but another part of it just keeps inflating. It just keeps going. And more little parts of the universe drop out and become regions of space like our own, or regions of space similar to our own but different in other ways, maybe different local laws of physics even. And that rubs people the wrong way. So this is something where we have our observations, we have our universe, we're trying to explain it, we come up with a theory to explain it, and we predict the existence essentially of other universes. And then the question is, a combination of science and philosophy once again. What do we make of these other universes that we don't see? They're predicted by our theory. Do we take them seriously or not? And that's a question that is hard to adjudicate by traditional scientific methods. We don't know how to go out and look for these universes. We don't even think it's possible, maybe, to do so. So I'm on the side that says you got to take your theory seriously until a better theory comes along. We can't say there are definitely other universes, but we can say it's very possible and we should take that seriously. Of course, it all depends on inflation being right, which is why people were very, very excited when a little while ago there was a claim by the BICEP2 collaboration, a radio telescope that was looking at polarization of the leftover radiation from the Big Bang, that they seemed to see a certain very, very faint signal, which is exactly what would have been predicted if inflation had happened. In fact, it was maybe a little bit stronger than you would have expected, but okay, we could find a wriggle room to make sense of that. People got very, very, very excited because it was the first direct evidence in favor of inflation, and that's sort of a too lucky to be true kind of thing. Like our meager human intellects apparently successfully reached back to the first trillionth of a trillionth of a trillionth of a second after the Big Bang and figured out what was happening. It turns out that it's probably not right. The better data that has come in since then seems to say that what we thought was a faint signal from inflation was in fact schmutz in the middle of the universe. It was stuff from our galaxy, dust and magnetic fields getting in the way. And you know what? That's how science works. We make observations, we interpret them, we make better observations, we learn more. So right now we're back to where we were. Inflation might be right, it might not be right, we don't know. Taking it seriously is definitely our job. One of the struggles that we have as modern physicists and cosmologists is that the conventional ways we have of talking about how to do science might be too simplistic. So one way that is very dramatic that we can put this is there is a t-shirt or bumper sticker sized motto that was given to us by Sir Carroll Popper about what demarcates science from non-science, namely scientific theories are falsifiable, which doesn't mean you can prove them wrong. It means that if they were wrong, you could prove them wrong. So a good scientific theory, according to Popper, sticks its neck out. It says, here's what I think is true about the universe. There's something very definite that I'm actually saying. If you look for this aspect and don't find it there, then that theory is not correct. And what Popper had in mind was sort of attacking things like Freudian psychoanalysis. He thought that there was nothing that a patient could tell a psychoanalyst that the psychoanalyst would not be able to say, yes, I have a perfect theory that would explain that. And Popper felt that if you could explain everything, you're explaining nothing. You're not sticking your neck out. So this idea that scientific theory should be falsifiable has caught on. And, Popper was not completely right about that. He's not really taken as the last word by any respectable philosopher of science, but he was on to something important. He really was pointing out that a good scientific theory should be carefully, definite. It can't have infinite amounts of wriggle room. But the scientists, bless their hearts, have taken this subtle piece of philosophy of science and kind of made it a little bit overly simplistic. So when we have a theory now like string theory, which says that there's little loops of string at a submicroscopic scale, or the inflationary universe scenario that says there are other universes that we can't see, these theories are saying something very definite. It's not like anything goes in these theories. But what they are saying seems to be inaccessible to our practical experimental abilities. Maybe even our impractical ones if you're talking about the multiverse that is further away than we can possibly see. So in some weird, overly literal sense, these theories are not falsifiable because we just don't know how to do the experiments to falsify them, even though they're saying something definite. So in my opinion, if you ask Karl Popper about that, he would say these theories are perfectly scientific. There's nothing wrong with them. I never said it would be easy to falsify things. I just said that theories should make definite statements. But certain zealous colleagues of mine are saying that because you can't see the other universes in the multiverse, or because you can't see the little superstrings moving around, these theories are not falsifiable and therefore should not count as science. I think it's a bit of a tempest in a teapot because, you know what, science is going to march on one way or the other. The overwhelming majority of physicists and cosmologists do not spend their time thinking about string theory or the multiverse. This isn't what most working scientists do. It gets a lot of public attention, but there's a small number of people who take these ideas seriously. I'm one of them. They will either pay off or they won't. They will either continue to be fruitful and drive forward new research ideas, or they will just sort of fade away and die. There is no danger to the scientific enterprise posed by people thinking about the prediction of inflationary cosmology that there are other universes out there. Sometimes the people, the cosmologists or physicists who talk about these speculative ideas, the multiverse, string theory, extra dimensions, and so forth, they catch a bit of heat from their friends and colleagues in the physics department back home because if you look at, the membership of the American Physical Society, the percentage of people in the APS who are working on these ideas is very, very tiny, but the percentage of popular physics books that talk about them is very, very large. I think that's fine, personally. I mean, I would think that. I'm writing books that are exactly in this vein. But, I think that the way that the person on the street is interested in physics is never going to match exactly the research interests of the working physicist. But the people on the street like the outcome of the typical working physicist because they build better machines, better technology, things that actually change their lives. The people thinking about the multiverse do not change anyone's lives, but it provokes us to think about our place in the universe. It's part of who we are as human beings. We should be asking these big questions. I think it makes perfect sense for physicists to share with the wider world their speculative ideas, as long as they're honest about the fact that they are speculative and maybe 50 years from now we'll know whether we were on the right track or not. There's something interesting going on where there's a whole community of physicists, who sort of advisors and students, have been doing theoretical physics with very little direct connection to observation. String theory in particular is like this. In cosmology, which is closer to what I've been doing, people are pretty close to experiments. We get new data in from the microwave background, from large-scale structure, whereas in string theory, there's been essentially no data or observationally oriented result that has changed the course of the field. And that's not surprising in retrospect. It's very hard. They're asking questions that are very far away from the energy scales that we can reach and accelerators. I do think that one could reasonably worry that they forget what it is like to actually try to match the data. The world is tricky. It's very rare that our ideas simply fit the first time the right way. And if you spend decades trying to come up with the right mathematical description of nature without worrying about fitting the data, you might forget that challenge and be satisfied for the wrong reasons. All the work done by string theorists could, in the end, mean very little. String theory is a weird theory. It sort of popped into our laps. Again, it makes predictions about energies that we have no access to in our current experiments. It might be wrong, but it's sort of amazingly good. Like a theory in physics has a feeling about it. It seems to make sense and work well and fit, or it just seems to crash and burn very easily. String theory kind of makes sense as a theory. It matches onto things that we think are true about the world. It seems to be very, very robust, very, very flexible. A lot of things can happen. It's hard to bring it down to earth. It's hard to connect it to the world we see. And I think that either we will bring it down to earth and connect it to the world we see, or people will lose interest. People cannot maintain this optimistic idea that we're going to get the right theory of quantum gravity, the theory of everything, if it's literally decades and decades of people writing down equations and never predicting the experimental outcome of anything. But we're not there yet. I think, it would be a terrible shame if we gave up on string theory when maybe next year someone will figure out how to bring it in connection to observations. Or maybe 10 years from now it will happen. So I think that this is how science works, and this is it at work. I think there's a great story about this woman, Princess Elizabeth of Bohemia. She is in a slightly different world than our world. She would be known as a great philosopher, but she was a woman in the 17th century, and there was no chance of becoming a famous philosopher. Her father was very briefly the king of Bohemia. So she became Princess Elizabeth of Bohemia, but then the 30 Years' War started, and they went into exile because he was on the losing side of the first early skirmishes. And growing up, her family, including her brothers and sisters, made fun of Elizabeth because she was overeducated. She was really very good at foreign languages and geometry and astronomy. They called her La Grecque, for the Greek. And in exile, she got to meet and got to know René Descartes, who was also in exile from France. He was accused of being an atheist because he thought too hard about the nature of God and so forth. And they struck up a friendship, but it was a sort of combative friendship because Princess Elizabeth didn't understand a fundamental part of Cartesian philosophy. And it's not that she didn't understand what Descartes said. She didn't believe it. She thought it was flawed. She said, you're a dualist. You think that there's a body, there's a mind, a spirit, a soul, separate, immaterial, separate from the body. But the body obeys the laws of nature, is what we would now call the laws of physics, right? How does this mind, this soul that is not made of material, how does it affect the body? How does the mind talk to? How does it causally influence the body? And basically, Descartes never found a satisfactory answer to this question. He tried. He took her criticisms very, very seriously. He imagined specific glands in the human nervous system. The pineal gland was his favorite example of a way that signals from the immaterial soul might be coming to you and giving you instructions. In the modern world, he would be very much against artificial intelligence. Descartes didn't think that machines could think, so he needed some way that the soul, the mind, could talk to the body. But it didn't really work. And I think that Princess Elizabeth's objections form a very solid basis for sort of inspiring the kinds of objections we have today to dualistic versions of the world, to theories of the world that put consciousness or mind in a separate category or box than the physical world. Everything that we've done in science for the last 300 years has given us reason to believe that minds, consciousness, are not separate from the stuff out of which we are made. It is an emergent phenomenon, if you like. It is something that happens because of the collective interactions between all the stuff that we are made out of. And I think that we're nowhere near understanding all of this. I think there's a lot of research to be done. A bunch of people, Stuart Kauffman, Prigogine, there are many people who've talked about self-organization and how things can come together, sort of individual mindless pieces can come together to make something that looks like it's thinking. But I would say that this is sufficiently ill understood that very few of our current ideas are going to last. I think this is a great fertile ground for young scientists to think about. Academia is a funny thing, of course. Young academics are, you would think, if they're studying physics or chemistry or biology or whatever, they're spending their time thinking about these deep questions of nature. Really, they're spending their time thinking about getting jobs, because there are many more graduate students who get PhDs than we can possibly turn into tenured professors. In my field, if you go to a really good place, Harvard, Princeton, Caltech, you maybe, if you get your PhD, have a 25% chance of someday being a tenured professor somewhere. And everyone knows that, and it causes for some nerve-wracking interactions. So in 1992, when I was still a graduate student, I got a phone call, and it was Stephen Hawking on the line. Sadly, I wasn't there in my office. It was Brian Schmidt, my office mate, who took the call. But Stephen wanted to offer me a job, a postdoctoral research job. And for various reasons, I ended up saying no. I went to MIT instead. 3 years later, again, Stephen Hawking offered me a job. I had applied all over for postdocs. And again, I said no. I decided that, I really needed to sort of go where I thought the hottest, best work was being done right at that moment, and that was at the Institute for Theoretical Physics at UC Santa Barbara, where it's a really, a amazingly, wonderfully interactive place in modern physics. And that was where I finally met Stephen Hawking. He visited Santa Barbara because that's where the good physics was being done, and he had come there with his retinue of graduate students. And one of the graduate students was Raphael Busso, who's now a famous professor in his own right. And I was talking to Raphael, and I said, you should introduce me to Stephen. I've never actually said hi to him. And as a joke, I said, I hope he's not mad at me because he did offer me a job and I turned him down. And Raphael said, oh, don't worry about that. There's this one guy who turned him down twice. And I said, yes, that was me. And Raphael's response was to run up to Stephen Hawking going, Stephen, this is the guy who turned you down twice. And that is how I got to meet Stephen Hawking. But the good news was that this is my second postdoc, right, in Santa Barbara, and I'm looking for a faculty job, a permanent position. What I realized was that back in 1993, when I was first applying, there was really nothing interesting going on in fundamental physics or cosmology. You could get by, you could be a hot property in the job market just on the basis of your promise and good letters. But in the meantime, while I was a postdoc, interesting things started happening. The second superstring revolution happened. We discovered the perturbations in the microwave background in cosmology. And the only people getting jobs were people working on that stuff. So I realized that in order to get a job, I would need to start working on something that other people thought was interesting, not just what I thought was interesting. Unfortunately, I was not an expert in anything that was thought to be interesting. All the things I was an expert on were my own quirky little interests that no one else cared about. Fortunately, in 1998, the year before my postdoc would have run out, my old office mate, Brian Schmidt, helped discover the acceleration of the universe. The fact that the universe is not only expanding, but expanding faster and faster due to what we think is called dark energy. This was a discovery in 1998. Brian shared the Nobel Prize for his efforts in the year 2011. But I'd like to remind him that in 1992, he was answering phones for me and picking up the phone call from Stephen Hawking. But the good news for me was I was the world's expert in dark energy and the acceleration of the universe before they discovered it. So suddenly I went from being ignored to once again being a hot property on the job market. And I got a wonderful set of faculty job offers. I accepted a job at the University of Chicago. And I worked hard on figuring out why the universe is accelerating. The bad news is I didn't figure it out, and neither did anybody else. So these days I've moved on. I think that, it's still just as good a problem as it was in 1998 or whenever, but it's hard to make progress on that problem. We need to take a step back and do a little bit more deeper thinking about the underlying rules of quantum mechanics and gravity before we're going to understand this problem. It's a very weird relationship that academics have with the outside world, with the wider world, especially in a field like particle physics, where, the last time that an experiment or a theoretical discovery in particle physics had any impact on anyone's sort of everyday life was probably sometime in the 1950s, when we were discovering muons and pions and things like that might possibly give rise to new technologies. These days, the reason we do particle physics or cosmology is purely for the sake of discovery. It's not for any practical application in the future. So really, we're being paid to do stuff because the human race has decided that these questions are worth addressing. And if we address them and then don't tell anybody what we found, there's no reason for people like me to exist. So I think that there's a great argument to be made that as a field, we have an absolute obligation to reach out to the broader public. This is part of the human project to understand our world, and we scientists are trying to contribute to that. And then part of that contribution is not only making the discoveries, but sharing them as widely as possible. And yet, within academia, there's no question that it hurts your career to write books, to go out there and to talk to the public. Both in, there's sort of two aspects to that. One is you're taken just a little bit less seriously because you're spending time, talking to the person on the street rather than to your academic colleagues. And, I'm a straight white male doing this, and I get, some disrespect for it. I cannot even imagine what it is like for women, for example, who do this, because they're already, looked with suspicion by the sort of paternalistic, dominant number of people in the field. And so that's one thing. The other thing, of course, is that when it comes to getting jobs and getting tenure, universities are governed by fear. They're very, very fearful. They will hire you, give you an academic position, and then you will stop doing research. And you'll have tenure and you'll be there for decades, and they will have wasted a slot on you. So if you let them believe that you have any interest in addition to doing research, then they will be worried. They'll be worried that you'll take up those interests and do them more full-time once you have your tenured job. So yes, you are doing research now, but once we give you tenure, you'll just write books and go sailing around the world or something like that. They're very, very afraid of that. So, I think it's very unfortunate. I think that we need outreach, we need education, we need public engagement and excitement. The public is there. They're ready. They like it. They are underserved by us talking about these wonderful ideas in physics and science more broadly. And yet, academia doesn't reward it. There are some people who will just do it anyway because we're stubborn and we like doing it and we think it's important. But I would be much happier with the future of my field if I felt that in a more systematic level, we were ready to support people who spent time and some of their effort doing outreach and talking to the public as well as doing cutting-edge science. So I'm sort of in a funny but wonderful position. I'm a research professor in physics at Caltech. There are very, very few research professors in the world at all, and very, very few of them are theorists. Usually a research professor is a job for an experimentalist working on some big apparatus or something like that. So fortunately for me, Caltech has a big pile of money that they're using to pay my salary. So I'm a professor. I have students. I could teach classes if I wanted to. I don't have to teach any class that I don't want to. So in many ways, for someone who wants to spend time also writing books and reaching out to the public, it's a wonderfully flexible position. And meantime, I get to do research, which, if there's any one thing, if I had prescriptions that I was only allowed to ever do one thing, it would be doing scientific research. That's what really makes me most excited. Writing papers, trying to figure out new laws of physics. But in my current position, I get to sort of take those hours of the day that a regular professor would use teaching or doing service to the university, and I get to use them writing books, giving lectures, trying to reach a broader audience. So that will last as long as Caltech tolerates me. It's very strange because if there are even other physicists who aren't reading my papers because they're not exactly in my subfield, a lot of them just don't know I'm doing research at all because, they don't read my papers, but they do know about my books. So, the books have a broader impact than the papers do. So I had colleagues who are surprised I'm writing books. I've had other colleagues who are surprised I'm writing papers. I like to think that the book writing, public outreach activities can be not oppositional to doing research. I have been inspired to do research projects by thinking about different ways of talking to the public. And I think that you can get the word out there even to your own scientific colleagues by writing a really good book. To me, the perfect popular science book is one that anybody can read, but your professional colleagues can read with enjoyment and getting some benefit out of it. That you're sort of talking about ideas in a way that they might not have heard of from you giving a seminar or something like that. So I think that especially in the internet age, we should go for the richest, thickest possible ecosystem of communication. We should communicate through books, through videos, through Twitter, through science publications, through seminars. These are not in competition with each other. They are all moving in the same direction.